right, thanks, Azalee, and thanks to the organizers for inviting me to speak. My name is Kate Alexander. I'm an assistant professor here at University of Arizona, and I'm going to continue the theme of multi-messenger astronomy by giving a talk that's actually very complementary to the talk we just heard, in that Michael focused a lot on the searches we've done for finding optical counterparts to gravitational wave events. And I'm going to tell you about an alternate approach, which is looking for the counterparts to these interesting rare gems in the radio, which has its own benefits, but also some of its own unique challenges. So why do we want to study multi-messenger astronomy? Well, we are very interested in the population of compact object binaries that exist in our universe. This plot keeps getting added to, but this is showing all of the mergers of compact objects that have been detected in gravitational waves or by other techniques in our local universe so far. A lot of them are binary black holes, but a few of them at the bottom are binaries containing at least one neutron star. And those are particularly interesting because we know at least some of them produce electromagnetic counterparts. Michael alluded to GW190814, which is, of course, our gold standard for a neutron star merger that definitely produced some light that we could see. But we still have a lot of open questions. We don't know if all binary neutron star mergers will be able to launch relativistic jets. We don't know if neutron star black hole mergers can do this. So really, we want to be able to find the counterparts to more sources. And as I'm sure many of you are aware, this is a very challenging problem for many reasons. We just heard about some of them, how difficult it is to pull out these rare gems that are these counterparts from large data streams. The one object where we've been able to do this so far, 170817, was really an extraordinary amount of luck for several reasons. One, it was nearby, so we were able to find a bright counterpart to it that made it a lot easier. It was fairly well localized on the sky. It was also visible at night. The object was visible just as the sun was setting, so if it had happened 3 weeks later, we never would have been able to find the optical counterpart. So we really want to get creative when we're thinking about going after these things, because the next time we might not be so lucky. So it would be nice to be able to adapt our search strategies to marginalize over the possibility that none of these things may be true. So for all the optical astronomers in the room, you're probably going, well, you can't really do anything about observing at night, right? That's at least something we don't have a lot of control over. But as a radio astronomer, I'm going to tell you that's actually maybe not a problem because our radio telescopes can observe in the daytime, so twice as much sky to look at all of a sudden. And fortunately, we do expect not only optical light to be produced when two compact objects merge. This is a fairly old cartoon, but it sort of nicely illustrates the different kinds of counterparts you might expect. We just heard a lot about this optical kilonova emission, but we also think these neutron star mergers launch collimated relativistic jets, which will produce a synchrotron afterglow that's visible in the radio. Depending on where you're viewing this jet from, this radio light may be delayed. If you're viewing it right down the axis, you'll see it immediately. Otherwise, it might be delayed and appear weeks to months after the transient. The same slower moving material that is initially neutron rich and produces this optical kilonova will also eventually shock and produce synchrotron radiation, but that can have a delay of years. So already we have a very different kind of problem if we are looking for a radio counterpart to these sources. Instead of a fast fading optical transient, we have a very slowly evolving radio component. And it's great if we can find it, because the radio emission does tell us lots of very useful things about the physical properties of the merger. We can learn, how much energy was launched in the jet. We can learn something about the ISM around the merger, how dense it was. And we can learn about the geometry, if we have a jet, how far off axis it was. These are just showing different light curves in the radio that might result from different types of physical properties of a jet. So what we really want is we have to really expand the time axis. We can't just wrap up our search and say, if it happens at the same time as the gravitational wave trigger, it's related. We have to continue our search for, a long duration. But there's also, so that makes it more challenging. But we're also helped by, several things along the way that make radio appealing despite this, having to expand the time axis. One is, we're less restricted in where we can observe. Daytime sources are no problem. The other thing is that the radio sky is much quieter than the optical sky. We've all seen images of the optical sky, and there may be hundreds or thousands of sources in your images. The density of radio sources on the sky is much lower. So we have already many fewer background contaminants we have to search against if we're looking for something variable. So we find radio transients today using a variety of telescopes. In order to get enough spatial resolution to, uniquely identify a transient with a particular galaxy, we usually need to use an interferometer, which is a bunch of radio telescopes all working together as a single large dish. We've made a whole bunch of computational advances recently that have allowed us to process large radio data sets from these interferometers in much closer to real time. So searches for radio transients are finally becoming feasible. And so we sort of have two complementary approaches that are ongoing for radio transient searches right now. One is exemplified by this radio telescope I've shown here at the top, called the Very Large Array in New Mexico. This is a fantastically sensitive, high-resolution instrument, but it has a tiny field of view, kind of a few arc minutes, few tens of arc minutes, depending on the frequency. So it's ideally suited for a galaxy-targeted search, like Michael mentioned, where you have a catalog of galaxies in the nearby universe, and you just point the telescope at each one of them, look for radio transients. There's also some new radio interferometers like ASCAP in Australia that do really clever things with their processing, so they can have a very large field of view. So you can do a single pointing, cover 30 square degrees on the sky, search that for radio transients. ASCAP is limited to lower frequencies, so there's a little bit more background sources we have to worry about, primarily AGN, but it's still a very promising way to explore the parameter space to do these searches. So, with this new technological capabilities, and some nice models that are, very simple models for how we expect the radio counterparts of gravitational wave sources to evolve. All we really needed was a good gravitational wave event to come along and provide a test case. And fortunately, we were lucky enough to have a good test case show up in 2003. So the paper that I'm going to talk about, for the next few minutes was using this particular gravitational wave event as a test case. This event is called GW190814. It may have been a neutron star black hole merger. It was maybe more likely a binary black hole merger, but at the time, it was a very promising candidate to try out, basically do a dry run on our radio search strategies to see if we could identify a counterpart, because it was very well localized on the sky. And at the time, it was not completely clear if this lower mass object was a neutron star or a black hole. So there was at least a mild possibility that it might have produced an electromagnetic counterpart. Now we think it didn't, but it was still a really excellent opportunity to do a dry run. So what did we actually do? Well, I had time on the Very Large Array, so we were restricted to doing a galaxy-targeted search. So we identified 75 galaxies in the localization region, which looked like this, that we thought were most likely to potentially host the counterpart to the gravitational wave source if it existed. We were able to cover about a third of the total stellar mass in the final localization volume with the amount of time we had. Not perfect, but good enough for a pilot survey. And we looked at each of these galaxies, 1 month after and about 6 months after. Given that this was a gravitational wave event observed highly off axis, we picked that time scale to kind of optimize the change in brightness that we expected to see. And so we took a picture of each of these galaxies, identified all the radio sources in all of our images, and then looked for sources that changed in brightness between our two observations to see if we could hone in on anything that appeared to be an interesting counterpart. And just to give you an idea of just how few sources there are in the radio sky, we only found about 75 sources in our 75 images that were detected in at least one image. We used a search radius of 100 kiloparsecs on the sky within each galaxy. So, searching a fairly small area. And then of these sources, 30 of them were variable according to our criteria. Those are the sources with the little plus signs here. We chose a very lenient variability criteria because we really wanted to dig into the noise. We cared more about finding that counterpart than about having a pure sample of variable objects. This was motivated by, we compared to our models how much variability we'd expect to see. And in some cases, we really wanted to dig into the noise to make sure we saw some things. And we were able to complement this with multi-wavelength observations. And we, in the end, found a couple of candidates that looked potentially promising, most notably candidate 1 with this red star. We were able to, however, use multi-wavelength observations at both optical and radio wavelengths to identify this as a background AGN rather than an actual counterpart. So using that, we didn't find anything in the end that was a genuine counterpart, which is as we expected. So we set some nice upper limits on, what we could rule out within this parameter space. So I think I have maybe 1 minute left, so I'll just skip to my conclusion slides. So I just wanted to sort of, summarize by saying, what have we learned from doing this exercise of going through searching for radio counterparts and, ultimately not finding anything. I'm actually highly encouraged because we were able to show that with a fairly efficient use of telescope time, we could in fact identify sources that had similar variability similar variability characteristics to what we would expect from a counterpart. And more importantly, we were able to then rule them out as candidates without doing a lot of expensive additional follow-up. A lot of them we ruled out as candidates by using pre-existing radio and optical survey data. So that right away just ruled out stuff using data in hand. And we were then, we did targeted follow-up, very quickly ruled out our most promising candidate. So I think we're really well set up now for 04 as we hopefully get some neutron star containing events. I think it'll be really important to coordinate follow-up. We're only going to get better as things like Rubin and LSST come online, give us better galaxy catalogs. And I think there's a lot of interesting complementary stuff the radio can do. So I will leave it there and happy to take any questions. Thanks.